as we observe the market maturing, we just see that it will become the new normal, that projects have to be able to reason about the evolution and the growth of their systems and the dynamics in a sophisticated manner. And in order to be able to do that, you need to have insight into how your system works, how it behaves in different situations. And this is really, I think, what we're trying to motivate you to do. And we're going to give you some examples. We're going to give you some processes. It's when we do these workshops, sometimes people get a bit disappointed because they're expecting like quick solutions. It's a bit like with fast food. I don't know if that's a perfect analogy, but fast food solves an immediate problem quickly, but in the long term, it's not going to lead to a lot of health. And we're more the guys who try to evangelize healthy nutrition. And so we won't give you quick fixes, but we teach and we apply in our own practices an approach that we believe is the best approach to create sustainable, healthy token ecosystems. And with that out of the way, I'll quickly go through what we're planning today. And then we'll kick it off. So we're going to tell you just briefly about BlockScience. This is not a BlockScience kind of pitch workshop. This is really about transferring content, so you can read about us in separate materials. And Dr. Zergam, are you on?
Yeah. Hello. Can you hear me?
Fantastic. Yes. Good morning.
Good morning.
I'm going to throw this right at you. I think this is the part that you wanted to take care of, yeah?
Yeah.
Dr. Zergam, so glad to have you here. Thank you so much for making the time.
Thank you.
Thanks, Rikai. Glad to be here.
I pretty much always start with a little bit of a discussion of complexity. It's sort of important because this is why token economics, token engineering is hard. There's sort of an inherent interconnectedness between our social and economic activity and the sort of in general, complexity would be we engineer things, we build new technology, we interact with the physical world, that world changes, and then as a result, the sort of incentives and our behavior changes to adapt around that changed world. This is rapidly accelerated by a sort of token system where your activities change the state of the network and as a result change the incentives. Your behavior is deeply interconnected with the sort of system state, and the system state has a high degree of influence on the sort of incentives you experience. Really simple examples are like surge pricing on Uber or the explosion of gas prices on Ethereum during the launch of CryptoKitties. You can just start to see ways in which the individual activity changes the state of the system, and the state of the system influences the sort of incentives or the material effects of behavior by people. And this kind of temporal dynamics is also the source of attempts to game or attack crypto economic systems or force them into states that are undesirable. And what we really need is a set of tools that can handle what I call closure under behavioral adaptation or adaptation. It means that you cannot simply assume that things are going to sort of work out how you plan or you prescribe them. There's going to be some set of things outside of your original planning that are not only likely to happen, but like are almost certainly going to happen. So in order to sort of address that, I tend to, I don't think, can you go to the next slide? In order to address that, I tend to appeal to sort of the history of various social and economic systems engineering topics. There's a couple different like patterns of thought that all share a lot of sort of central tools. They are coined at various points in the last century. We've got cybernetics, was actually coined in the 40s and refined in the 70s. Socio-technical systems was coined in the 50s. And I tend to really highlight and work around this concept of cyber-physical systems. If you were to look at the Wikipedia definition of cyber-physical systems, you'll see that it's defined as mechanisms that are controlled or monitored by computer-based algorithms and tightly integrated with the internet and its users. It's pretty hard to argue that a crypto network is anything other than a cyber-physical system. And as it happens, the sort of cyber physical systems literature accounts for highly networked, highly interconnected systems such as sort of power grids. And they're actually some of the most relevant sort of mathematical systems for understanding sort of what happens when a system has sort of both interconnections with human activity, the consumption, as well as sort of physical, partially deterministic elements. In this case, we're talking about the physical network itself. And actually, there's real considerations for adversarial behavior. And that basis is something that's really motivating for our methodologies, for our tools. We're not just sort of pulling out things that are hyper academic in the sense that they're used for, writing papers. We're talking about the sort of mathematical and methodological approaches that are used to build real things in the real world when there is real complexity and there's real uncertainty and there's real risk of adversarial behavior. I hope that makes sense. I'm usually pause for a moment to make sure I'm not losing anybody. We're sort of on the same page here.
Yeah, I wanted to also mention, if you guys have any questions, feel free to interrupt us at any time. We hope to make this as interactive as necessary. And also there is quite some background noise. If the person who's out on the street could just mute him or herself, that would be probably awesome. All right, let's move on.
So in practice, in order to accomplish this type of sort of work, you need a pretty big mix of expertises. And we worked pretty hard to build relationships with other groups and to hire some of the best people that we could find. I tend to highlight this sort of synergy because it's not something that you can necessarily do with one person. And I think maybe that's sort of a common pattern in a lot of sort of tech. We tend to look for unicorns and we have to say, oh, someone needs to be able to do all of these things. And in practice, it makes actually more sense to build a team. And that team needs to have collectively an understanding of the sort of finance and economics and the sort of decision science, mechanism design elements that I think are most often associated with crypto economics and token engineering. But what we find is that it's really important to have an understanding of a few other topics. In particular, I was just talking about the cyber physical systems, and that tends to come out of the sort of information systems, AI, automation, and robotics groups. These are places where the cyber physical systems research and development and maintenance and operations are all actually rooted. I think that some of the methods that are most robust to uncertainty and most robust to adversarial behavior don't actually come from the economic literature at all, because the economic literature has had a long history of very fuzzy sort of success or failure outcomes. And the robotics and automation, the sort of aerospace and defense fields actually have a much tighter feedback loop in terms of whether or not the systems that they're building actually have the intended properties. You can think about that as if you screw up designing a robotic system based on the methods related to, say, the uncertainty in the environment, then it's going to crash into a wall, and you're going to know that immediately. And as a result, you're going to be able to continue to refine your algorithms. Economic systems tend to fail slower and less concretely. We tend to wave our hands around a bit and say, oh yeah, it totally worked. And that's a problem from a fitness and from an evolution standpoint. So the evolution of the knowledge about how to do these things actually is creating a fitter set of tools and methods in environments where failure is a little bit more is a little bit more concrete. I also like the literature, some of the game theoretic literature that's forked off of the economic game theoretic literature in the 50s and 60s. Was applied heavily in the defense industry, and as a result is associated with things like missile targeting and other environments where the cost of failure is considered very high. And that strongly impacts the way that the algorithms and the methods and tools evolve over what is amounting to 5 to 6 decades. I find that in particular those frameworks and methods are a little centralized in their nature. So it's also not completely the answer. The most modern methods in AI, and particularly multi-agent robotics and coordination, actually are bio-inspired. There's a really strong mimicry of signals and systems patterns that appear in nature because they're inherently decentralized. They're robust to all sorts of failures where you have a swarm of robots and a dozen of them fail, all of them but 3 fail. In theory, the other ones are still able to work together. And in practice, obviously, depending on the size of the swarm, the system basically behaves functionally the same with with a large fraction potentially, not working as intended. It's a little bit tricky because you're getting into this question of, at what point is it still the swarm, which is similarly like, well, how small does your market have to get before your agent-based model ceases to behave systemically as you designed it to? There's a lot that you can start to unpack here. There's also other algorithmic sort of natural signal processing things in biology, from the way that we look at action potentials with neurons building up to create continuous to discrete transformations that in neural networks. We've actually used that in a crypto economic design. It's using this sort of recognition that biological and like human systems that exist today, if you get a good model of them, they're representations of things that work. And you can't overstate the importance of mimicking patterns that you've already seen in flow, because it turns out that many things just don't end up behaving the way that you think they're going to. So having something to essentially bootstrapping off of nature can actually go a really long way. And so I'll kind of wrap up this slide by kind of going back to the sort of the far right. The purple bubble is talking about infrastructure, supply chain, and sort of, civil and aerospace, like real, like hardcore, physical systems engineering, because I think we tend to forget to design for full life cycles. A lot of time with crypto, we talk about sort of design and deployment, but not necessarily like the operation and maintenance and end of life of a system. There's no like really truly permanent system. It might be that your system continues to exist in one form or another. You could argue that something like Bitcoin is going to last forever. I would tend to agree that it's infrastructurally, as long as people continue to run nodes, and even if someone spun up a node 1 million years after stopping, it would continue to persist. But you can also imagine it as having phases of its life and understanding how it can change systemically over the course of those phases. You can consider the period before the pizzas, where it was really just a hobbyist's thing, and you can ask, like, what was that system like? You can look at its cycles as it's sort of, spun up and down through a market adoption and that future market adoption that we all sort of expect. But then you can also ask, what happens when the mining rewards drop to the point where they're not really a driving source of value anymore, except for the transaction fees? And does that change the way the system behaves? Like, do we really know? Not really. But that's a meaningful phase shift. And so really that engineering discipline is quite good about accounting for systems, not just at their sort of design and deployment, but also understanding their sort of operations, maintenance, and failure modes, and what end of life conditions look like. And I think that sort of getting these sort of 4 areas into your mind are a good way to access the knowledge that exists today. Make sure that we're really not building from scratch, and taking what we already know about building complex systems and applying it to these token economic systems. So Jonathan, I think it's back to you.
Cool, thank you. So this was a bit of an introduction that we like to put there because it's important to just understand where BlockScience comes from. There is the standard kind of light introduction to what we're offering, and I just quickly browsed through, but this you can really read on your own. So we're a company, we're based in San Francisco. We're about 20 to 25 people, I think, at the moment. And we specialize on the design and analysis of these complex networks, right? If that wasn't clear. And really our secret sauce, and you can read through the stack and what clients say about us and so forth, but is that we have a team that is experienced in engineering very complex systems. In other domains, for example, Dr. Zergen mentioned swarm robotic systems and so forth. And we apply these approaches to the blockchain ecosystem next to other areas. We're not only working in this space. What we end up doing in most cases is we end up creating digital twins of these network ecosystems. So what we realize is that at some point, most sophisticated projects, they come to a state where they just want to be able to understand their systems and play with the system dynamics, look at the outcomes of these complex dynamics and tweak the systems based on these observations. So we create digital twins, which are sort of virtual replica of systems, for example, blockchain based systems, and then this allows projects to gain insight into their real world systems. So this is in a nutshell what we do. We have here you can see a couple of the projects that are public that we work with. There's a couple of more that, and Web3 Foundations is one of them that we can mention. And we have quite a sophisticated process, which all engineers do. This is something you might want to look through, also to get inspiration for how you approach these things in your own projects, even if you do not have external help. So many projects, they ask us to guide them through this process, and then we are sort of end to end with them. But many projects also try themselves, and I think it's helpful to just know that there is typically, if you want to design something as complex as a cyber physical system involving blockchain technology, that you want to go about it in a very structured way. So we typically start with just gathering the requirements, and then you can read through this. This is not what the workshop is all about. Okay, so I just wanted to throw this out here, and I think it was pre-sent yesterday. So let's go back and now go to the core of this workshop. Zergen, do you want to share your screen? I think there's quite a couple of slides you want to maybe direct yourself.
Let me hold on. I need to open it then because I was following on yours. So.
We put the slide in here so we don't forget to ask for questions. Did that make any sense at all? Do you guys have questions? I know this was sort of a bit of a hardcore introduction to BlockScience, but we rather say straight out what we're all about.
Any questions, guys?
No, not for my part. Dave speaking here. Sorry. I think it describes, it gives scope to what we're heading to, and I think there's a lot of reading to do after the session. But I've got a good impression from to where we're heading. So no questions for me.
Great, thank you. And I think what you said is right. So as I said, I think the goal is to motivate you, to give you the scope, and then you can dig into the topics that you find most relevant in your specific project phases. Okay, so I'll stop sharing. Zergen, if you want to share your screen, then you can roll.
Right. I am sharing. Let me make sure we get into slideshow mode. Can you see my screen?
Yes.
Okay, cool. So we are now going to talk about the sort of core of the material. This is going to be a little bit more on the theory side, and it's going to work its way into the practical side. So bear with me a little bit if it seems like it's me teaching an academic class. Admittedly, it's actually kind of set up like that. The point is to sort of establish the basis of theory and then apply it. So we work with this sort of scientific process. I will say that this is sort of a practical scientific process in the sense that we take theory, we use it to create simulations. This is essentially what CAD is. So in any engineering discipline where computer-aided design is an element, that is simulation. So you create an abstraction or a representation of your design, which is technically theoretical. You embed that representation or that design in a software system that emulates it or simulates it, and then you develop and deploy something, and you use empiricism to measure the current state of that system, and you compare that empirical data back to your simulations, and you use it to refine your theory. And this creates a feedback loop of ever increasing understanding of your system. Now, obviously, in a system like the ones we're talking about, you aren't going to be able to necessarily massively change the system that you deployed. And that means two things. One, that there's an extra amount of sort of, dependency on your initial sort of design and your initial sort of validation through simulation. And the second is that your ability to maintain and monitor and take care of the system that you built becomes very important. So the empiricism element actually comes into using data, interpreting it in the context of your system model to sort of assess the overall health of your economy at a level that goes beyond just, hey, what's the market price? In this particular setting, these are really three kinds of scientific results. And so if you have worked in a scientific domain, you've probably done research in one or more of these ways. Analytical is what people in very mathematical disciplines do. They make formal assumptions and they make formal conclusions from those formal assumptions. And that's actually the basis of a lot of both economic and engineering decision theory. You flesh out a set of assumptions and then you make proofs and statements about what is true conditioned on those assumptions. The real challenge is that often our assumptions deviate from reality a little too far in order to be concretely useful. It's one of my main criticisms of a lot of the economic decision theory is that due to the things I mentioned earlier, they weren't necessarily like hard, refined as rigorously as the engineering equivalent. So their assumptions are less likely to be true, and there's a little bit more tolerance of representations of the world that just aren't that useful. And then the conclusions that are made from those representations of the world are, like, unfortunately a little less useful. I'm happy to say that we do have stronger results that depend less on concepts like whether someone is, perfectly rational in an economic sense, but unfortunately they're also much harder mathematically. The running joke is that this kind of split between the sort of economic game theory and the sort of aerospace and defense, sort of what became the AI and robotics version of those things, split based on how hard the math was. Maybe that's not very nice, but it's at least the thing that the AI scientists say. But anyway, so moving along though, it's important to understand that the next step in that process is computational science. And computational science is about taking formal assumptions and producing data. And part of the reason why I was making the comments about the analytics is because, in fact, taking them to the next step and refining them with computational experiments is a really important way to sort of verify and refine those assumptions that you're making. If you're getting results that don't make sense or don't kind of jive with the real world, then you know that you don't really have the right thing yet. And so we can do analysis in the sort of data science sense to reach conclusions, but actually we don't have formal outcomes, we have data. And that starts us on the path to our empirical science, where we have measurements and observations which generate data. So you can kind of see a overall trend from theory, formal assumptions and formal conclusions, to sort of something more practical, where computational is formal assumptions yields data. And so then we do our sort of somewhat subjective analysis to reach conclusions. And then we have empirical, where we've made whatever measurements and observations we can, which produces data, and we can have analysis to reach conclusions. And once you close the loop between the three, you can get a pretty complete picture, even in sort of complex or uncertain scenarios. I'm going to press through this slide instead of trying to talk through it one slice at a time. I tend to come back to this concept of complexity and try to make a point about how to break problems down to understand them in what I will call the right chunks. We have this scenario where the social, economic, technological, and potentially physical elements of a system have historically been sliced apart from each other into silos and analyzed in the silo. But when we're talking about networks, especially these social and economic networks that are enabled by technology, it becomes a lot more reasonable and works a lot better if you slice it horizontally rather than vertically. So we don't say, well, tell me about the economic system. We have to understand, okay, well, what are the social effects? What are the economic effects? How does the technology come into play? You know, if we have a physical element. And to be clear, in crypto networks, I generally think of the physical element as the hardware itself. So the running of nodes. And if you have limitations that are drawn from the sort of actual network itself, I would bundle that into physical, whereas technology here is more like the algorithms, the smart contracts, etc. What you call these buckets might change depending on the problem framing. The highlight here is that instead of segmenting these problems away from each other a priori, we start with the question of, okay, how do they interact with each other? But once you do that, you've kind of, you got to be careful because you can't do everything at once. So we slice it horizontally as a way to make the problem sort of parsable again. And I tend to work from top to bottom from a goals perspective, but from bottom to top from an enabling perspective. So we'll say that the goals of the ecosystem that you're designing are going to be sort of value flows, that value flows through the network in a certain way, in a sort of macro sense. And the individual agent behavior is the thing that actually creates that, but it emerges from the individual behavior. You might have macro scale phenomena that are inherited from the micro scale behavior, but isn't actually like clearly linked in the sense that you can say, oh, if this happens, then that will happen because of the interaction effects. As we move down, though, the local agent behavior is not totally free. It's determined by a set of mechanisms and even incentives around how to use those mechanisms. I tend to highlight the difference between incentives and mechanisms as incentives are like sort of related to individuals achieving their some goals, even if they're private goals, whereas mechanisms tell you what you are allowed to do. They don't tell you what you have to do. And so you never have to do the thing that you're incentivized to do. If you want to spend more money than you're making, you can do the opposite, but you can't do something that's not allowed. So I could give away all my Bitcoin. As long as I have it, I can use the send mechanism and send it to people, because the only mechanistic constraint is that I can't send Bitcoin I don't have. It's a no double spend rule, and that's a functional conservation rule. So a send is like an interaction pattern. It's a very simple one. We can have much more complex interaction patterns in designed economies, but I find it's really important to separate the notion of what I'm allowed to do under a mechanism and what I'm incentivized to do. That's the jump down from the behavior to the sort of patterns of behavior or the allowed behavior. And the way that we can actually enforce what's allowed is through trusted computation. So in the case of Bitcoin, obviously, they're a very simple set of mechanisms. They're essentially hard-coded into the network. But if you take something like Ethereum, then you have much more general cryptographically guaranteed execution of code. You write a Solidity program. It runs whatever the program said, maybe not necessarily what you intended. You have to be careful because code does what you tell it to do, not what you want it to do. In this case, though, we're saying that whatever it is that you coded is cryptographically guaranteed and backed up to durable data, or like data that's stored in a blockchain or in a content addressable DHT, or in other words, has a sort of a durable or like physicalness to it that, historically databases and sort of data in the internet in general is not necessarily considered to have. And so if you work all the way down to the sort of bottom of the stack, you see that we have this sort of trusted data and trusted computation. We have, the state of the system, moving up to the ability to mutate the state of the system in a trusted way, to the patterns for mutating the state of the system in accordance with a design, up to the actual behavior that's actually exhibited over those mechanisms, all the way up to the sort of macro dynamics, the things that we are actually designing for. And if you really take the time to break it out like that, one, it's really incredible what we've managed to accomplish with these technologies, but also you can start to see that you don't get the jump from the bottom to the top one for free. This whole idea that you leverage trusted computation to design interaction patterns that sort of incentivize certain local agent behavior that emerges into a desired global behavior is still a pretty big leap. And that's one of the reasons that we talk about the cyber physical systems, because that leap is most akin to being able to design things like, my favorite example is power grids, where we know how electricity flows. No one can, mutate the state of the system in a way that violates physics, but at the same time, getting the system to have the right amount of power production for the right amount of power consumption and avoid cascade failures in the network if there are, large fluctuations, et cetera, is actually a really non-trivial engineering challenge. So kind of pivoting the same discussion to sort of thinking a little bit more about technology, I tend to review the sort of blockchain enabling of these systems with a focus first on what you're designing at the network level versus what you're designing at the ecosystem level. So we've got actually two networks embedded in each other. The lower level network is a peer-to-peer communication and computation network. That's your actual blockchain network. And it's defined by a set of protocols, potentially network configurations. If you have a permission network, there are access controls, there are transaction schemas. You can design a pretty sophisticated data model and rules for validating that data model and validating that people change that data model according to a legal set of transactions in this sort of right half of this diagram. But what's interesting is that we can view that computation and communication and computation network as an enabler of a social and economic network, and that social and economic networks links are actually the behavior of agents with respect to each other, or even in some cases you could model it out as the relationship between contracts and each other. When you have lots of interdependency and function calls in, say, Ethereum contracts, there's actually a network of interactions first at the level of the contracts that adds another layer to this. So that network, and then on top of it is the agent behavior. And so you start to see this sort of nested pattern of networks inside of networks, not necessarily because you need to think about all of that, but because it's important to think about which layer you're in. Some people are working on things that are most closely associated with the social and economic network. Some people might be working on some smart contract. A lot of the DeFi stuff fits with what I was saying about the interconnectedness between smart contracts. And some people are working on protocol level designs. And it can be dangerous to not think through which part of the system you're dealing with, because if you apply learnings from others in the wrong layer, you might accidentally, do something that you didn't want to do because you thought, oh wow, this really worked for somebody. But actually what they were doing was related to, say, the interconnectedness of smart contracts layer, not necessarily the sort of user behavior layer. And one of the reasons that these are different is because the actual actors have different characteristics. You need to make different assumptions about how they might behave. A piece of software acting as an agent is much more likely to behave like a rational agent than a sort of end user of an application. And so it's key to understand context, to make the right assumptions, to build the right models, then sort of inform your simulations, inform your testing, and even inform your sort of user experience design on your final product. So I'll probably jump through these parts pretty quickly because I think the next two slides are hopefully within the sort of space that you guys already understand. But I tend to dive in on this lower level where we talk about transaction ledger schemas, access controls, network configs and protocol specs, and like what does it mean to build the lower level network and really align it with a natural ontology of the system that you are representing, because we have a tendency to just like put things in blockchains, and in practice we might actually want to use content addressable DHTs for some of the information that's higher volume or potentially needs to be accessible even if we're not necessarily validating it at the same level. You also might need to worry about access controls and permissions if you have any sort of enterprise touch points. I basically like to say that lowest level isn't one size fits all, and it's just what's right depends on the sort of ontology of the problem you're solving, in the sense that if you need a ledger like say Bitcoin, then it's great to have what we like to call the triple entry accounting, and the sort of real time it's essentially verifying transactions before they ever happen. From an accounting perspective, it's amazing, but that matches the ontology of the problem. If you had a different kind of system, that could very well not be the right underlying data architecture. And one of the data architectures that I like to highlight is I call attribution and attestation, which is something a little more inherently subjective, but it's really important to maintain the provenance of the facts. So you're saying, I got this from here. That's a reference. And in content addressable DHTs, you can do one-way referencing very effectively, because if you have a pointer to another content address within a piece of content, and then you address it using a hash, you actually can't mutate the pointer. So you get a really rigid set of references. So an example would basically be, you can't delete your tweet. If you tweeted the thing and you content addressed it and you posted it, it's permanent. And if someone references it and says, hey, this person said this ridiculous thing, then there's no way for you to later then change the pointer or change the thing it was pointed to, because all of those things are interlinked using a technology that doesn't allow for mutations without becoming a new thing entirely. And I personally am a huge fan of the content addressable DHT technology as a very primitive tool. I think it actually gets a little not enough attention relative to blockchain, because I actually think it's one of the main ways that blockchains become not just overblown databases, because you can keep track of things like permissions to access, or you can keep track of pointers or things that are not too big to belong in blockchains, and still sort of reference the data in a content addressable DHT in a sort of cryptographically enforced way, because there's no way for you to get something other than the thing that's been addressed. There are also questions of availability, and it's not a one instant fix for everything, but it's important to understand that it belongs in this technology stack in a pretty consequential way. I already spoke a little bit about the idea of trusted computation and interaction patterns, and separating the notion of can do from will do. In particular, I want to bring out a notion of externalities. So one of the most powerful tools in crypto economic design is internalizing externalities. So a lot of inefficiencies in economic systems come from someone exploiting externalities, that in particular the negative externalities, where you get there's a hidden cost that's borne by someone else. In these systems, though, you can embed that in the transaction by modeling the externality into your system, and then estimating the effect of the externality, and then in changing the cost of the action to account for the externality. You also have positive externalities. Positive externalities generally drive network effects. And you don't necessarily need to internalize a positive externality because you want the effect that it's going to bring. But in principle, you can model a positive externality into your system and actually reward someone for creating a positive externality. So in this sort of diamond example here, a consumer is going to consume a service S, and they're going to pay a quantity Q in tokens for that service. But we are going to imagine that we've modeled both a positive and negative externality that is associated with the consuming the service S. And so if you say, given my action S, I'm going to incur a negative externality L and a positive externality C, then what we actually do is change the amount Q as a function of those that incurred liability, that negative externality, and that positive externality. So this is a little tricky, but the way that you can think about it is you can state a conservation law that's a function of the service, the payment, the liability, and the sort of positive externality. And then you say, okay, well, I'm going to make you pay the amount Q that preserves this invariant, or better yet, maybe if this is a penalty function of some kind, reduces it. And I won't belabor this too long, but this is the kind of design pattern that actually decentralizes, because as a conservation law, it combines very effectively. There's no way to cheat it by saying intelligently running in front of other people or changing the orders. The conservation law holds regardless of the order. That doesn't mean that there's not some effects agent over agent where someone, say, front running someone might get some benefits, but it does mean that that those sort of micro interactions don't violate the macro property, because the macro property, much like your no double spends rule, is actually a global invariant inferred from the local rules. In particular, this example was constructed for the sustainability space, done some collaboration with Sean Conway, who's the head, head of IXO, which is a sustainability-focused blockchain building on Cosmos. And there's a lot of questions about like how we manage internalizing externalities when you're talking about sustainability systems. I wanted to sort of zoom back out now, since I've been talking about a lot of things in the weeds, and make this a little bit more practical. So this is a standard engineering methodology. Pretty much every systems engineering textbook in any engineering field, from aero to civil to, you're gonna see a version of this thing. It's a validation and verification V. It's very stylized with the V shape, but we're basically saying that you need to capture the system requirements. You need to be able to take those requirements and convert them into designs. And as a result, we're sort of going to work our way down into the subsystems and the components. We're going to iterate over the designs and the components, and we're going to sort of fill out that system architecture. And we're going to then start to implement the components and recompose them, like build them up into a system. And this is where a lot of the challenge comes for people who don't have as much of engineering methodology in their background. The software world has a tendency to sort of do design and development all together. And that works great at the subsystem and component levels. It starts to break down at the system architecture level, because there's a sort of multi-phase process going on. You design the system, you break it down, and then you can follow that faster process on the parts. And then you have to go through a sort of outer process to verify first that the parts themselves work, and then verify that they work together. It's a little bit cheeky, but I say that sometimes that some of the crypto economic designs I see are a bit like airplane parts on the tarmac as opposed to an airplane, because people have done a really awesome job building parts that they understand, but they haven't quite gotten the hang of how to compose them together into some whole thing that achieves the top level goal. And in particular, when we're dealing with complexity and emergent behavior in social economic systems, I refer to this as the emergence chasm, because you actually cannot prescribe the desired behaviors explicitly. Like, we talk about incentivizing people to do things, but incentivizing is not programming. They will not do those things because you said so. So there's an extra level of uncertainty around whether you get the desired outcome. And the only way to really address this is to iterate, and to iterate on your designs, on your system level designs. The computational experiments serve the role of asking whether your system architecture is going to have the desired properties or close to them way before you get through all of these cycles. Because if you're wrong with your system architecture, then no amount of better part designs is going to make the whole system have the desired properties. So I talk a little bit about computer-aided design. I'm going to just fill this all the way in. So in the case of crypto economic systems, and in general in the case of engineered systems, we have our sort of CAD side of the simulations, which is where we have our original sort of differential equation based representation of the system. It hasn't been implemented yet. And we use some pretty high level assumptions about behavior. And in this case, we're usually doing, rough modeling, like, hey, does this make sense? Does it work right? Sort of on the far left. And as you sort of get a feel for it and you understand that, yeah, okay, our design is right, you can sort of make that design richer. You add, more exhaustive experiments around individual agent strategies, but you're still running these experiments against what is a representation of the system, a model of the system. And that's this stochastic differential equation, or this differential game where the agent behavior is this sort of uncontrolled input, this uncontrolled action that is, out of the control of the designer and under the control of the participants. Once you have those models and you use them to inform the development of actual product, then what you actually want to do is repeat those experiments using your product as the system. So the differential equations are a digital twin of your real system, and the real system itself is sort of fact-checked against that. And the reason that we use the term digital twin is because in the physical sort of engineering sciences, you almost always have a representation of the thing that you build in order to sort of cross-check with it. So whether it's testing for earthquake resistance for a building, whether it's maintaining the health of an airplane, whether it's, I could go on. Point is, you actually have a theoretical abstraction and a software implementation of that abstraction that you feed data and that you run experiments on in order to operate, maintain, sort of manage the health of that system. And we do this for crypto economic systems using our Statespace Modeling framework. The Statespace Modeling framework is really an adaptation of the existing sort of robotics and control Statespace modeling frameworks. I have really made one major shift, and that is to decouple the concepts of mechanisms and policies in a slightly different way than they're decoupled in control theory and robotics. The main difference is that I'm not in control over the behavior rules. In controls, you have a plant, a system model, which is the f of x and u on the right, and it's called the plant because it's the thing that you're controlling. So I wonder, actually I think that this is derived a bit from the chemical engineering discipline, which was, actually it's a bit of a tangent, but point is, it's called a plant, regardless of the reason that it came to that name. And then you have the controller. And the classical representation, the controller is under the control of the designer, and the designer designs the controller to cause the intended behavior on the plant. In the crypto economics, token engineering version of this problem, you actually get to design the plant, but you don't have control over the controller, because the controller is the agent's behavior, their response to incentives, and it's driven by their private signals, their private beliefs, and their private objectives, which you probably don't even know. There are cases where we can make, hey, they're going to be rational in some financial sense, but you actually can't guarantee that because it's not under your control. They may choose to act otherwise. Interestingly enough, though, we can make meaningful mathematical statements about how these systems are going to evolve by leveraging the plant design rather than the control design, even accounting for all possible legal controllers. The paper that's linked in the lower left was a Statespace Modeling academic paper that I wrote with a professor at University of Pennsylvania and one of his students. And we basically mapped out an example showing that you can even model the Bitcoin network this way by pointing out that there's the balances in the social and the economic network are essentially the states of the system that have a robust mechanism, no double spends, and that regardless of all possible send actions over time by all of the participants, you can still guarantee that Bitcoin sums up to the sum of all mining rewards, which we all sort of know is true, but being able to show it makes it clear that that is a globally provable property, and in fact, that property is what imbues it with its ability to function as a ledger for a global asset. If you didn't have that property, no amount of other things would make up for it. It's the reason why previous versions of digital cash really didn't hold up. Building off of that work and using this framework, actually, that student just finished his master's thesis. I think he just submitted it. I'm pretty sure it's circulatable also. It's a set of computational simulations of a crypto network using this framework. I'm going to move on for now since our examples are going to come from a couple other projects. So I'm the designer and architect for a project called the Common Stack, collaborating with Giveth. And I'm probably not going to go to this in hyper detailed because there's a lot going on here, but this is essentially a funding distribution system. A lot of times you would refer to this as a DAO. I tend to error away from that because the system is really not just the software system, it's the software system and the people interacting with it. And I think that the term DAO tends to underemphasize the human behavior element of the system. So this is our commons design, and it has a bonding curve as an interface to the outside economy. Its token is a private asset essentially to the community. Anyone can participate in the community by bonding into it, but we don't interpret the token as a sort of global asset that's going to compete on the stage for the notion of money, but it's rather an element, a programmable, specialized asset that's useful for a participant in this community. And you basically bond a reserve currency, here we're talking about DAI, in order to get some of this special local currency. And you can kind of thinking about it like you're going on vacation and you're going to go to a small island somewhere and it has some local currency and you trade in your US.E or your euros or whatever you're using, and you get some local money and you spend it while you're there, and you need to have as much as you need to participate in that community, but you don't need more. And here, instead of traveling somewhere, we're just talking about your attention. So how much of your attention is going to be contributed to this community? How much, asset do you need to participate in that way? Then that's the thing that's going to dictate how much you bond in. But interestingly, this does mean that that economy will grow as the community grows, as the amount of attention that that community pays to this system grows. You still get a growing economy. It's just that you're not growing by trying to take on this, transaction volume per se, or this, roll of money per se. You're just saying that, if in order to use this functionality in these smart contracts, you're going to use the assets that are programmed to interact with that functionality, and thus they have some managed value associated with the bonding curve. The rest of the system contains a voting mechanism called conviction voting. There'll be an article coming out about it very soon. We can happily forward that to you guys, and basically a proposal management system that's built off of the GiveFDApp, actually. So that's the sort of anchor. It's saying, hey, you can allocate funds into proposals, and then those proposals can hold those funds and issue them according to milestones. This whole system, though, is only healthy and sustainable insofar as it produces material outputs, because it only really makes sense if it has capital to allocate. And, you know, one of the biggest outstanding questions is, you know, what does it need to do in order to either generate revenue or to get continued sources of grants? And because this is a design pattern that depends on what the commons is going to be associated with. We have plans to launch more than one with different communities, and it really becomes the community that using the commons that dictates the value creation and thus the sustainability of that system. I will sort of highlight the fact that that's an open question, right? You can't just have this thing live forever for no reason. It can't make value out of nothing. I kind of like to describe it like the community center as opposed to the community. The community is the people. The community center is the infrastructure, the building that the community lives in. And it's traditional in architecture to think about how a space enables people to accomplish a set of goals, but to understand that it's not the space that's accomplishing the goals. And so with a DAO design, it's actually very important to understand the DAO, the contract infrastructure is the building, and it's the community in the building that actually makes it, you know, air quote, autonomous. So quick sort of look at what kind of work goes behind something like this. The trigger function is a sort of critical element at the top of this. So that trigger valve is what decides whether funds get released. So I have a plot over here on the right sort of showing that the trigger function is actually designed to diverge as you approach a maximum. So this is an analytic property that's derived. We don't want it to be possible to take more than 20% of the funds. So the amount of conviction required to take 20% of the funds actually diverges to infinity. And that's encoded in the design. It will appear in the smart contract. It will also appear in the simulations to demonstrate the property holds. More generally, I have on the left here what I call a business logic differential equation, or a generalized differential equation. So policies are the uncontrolled activity, and the variables bucket has all of the state updates in it. And what we're saying is we've decomposed a sequence of chunks of action, consequence of action, action, consequence of action. So this is that Statespace modeling framework actually in a design embedded in a CAD model. And so this system obviously has a lot going on. We have some random driving processes where participants arrive or leave. We have to update the network based on the funds that they buy in or sell out. We have a bunch of projects running, and we can check their progress and basically flip coins to see if they're completed or not. In some cases, they can fail. That's sort of a driving process that's modeled. And then we have the trigger function, which is the design that I'm showing you on the right with the 20% max and the sort of required conviction exploding the more you want. And then we have the actual individual participant decisions, which are based on actually some private signals, like their sentiments and preferences are generated randomly for these simulations, but allow us to see the consequence of certain assumptions. And so we build out this sort of differential equation, this business logic differential equation. We set the simulation parameters, which you can see in the upper right. We set the initial conditions that you can see in the lower right, and you get results. So this is a sampling of outputs from that system. You've got proposal statuses, we've got token prices, we've got our bonding curve holding on its invariant, and we have a snapshot of the holders and their holdings, their preferences being broadcast, and sort of how the proposals are charging up with conviction. I'm not going to try to parse through every one of these plots, but it's meant to show a sort of overall sense that this whole system model embedded in a CAD sort of generalized differential equation or business logic differential equation lets us see the very like nonlinear consequences of the interaction effects of these different mechanisms. Because, you know, a lot of times people talk about mechanism design one mechanism at a time. And it turns out that it's just not a valid way to analyze it, because in hybrid systems, it actually, there's a well-known like theorem or proof that says that if you have two stable systems and the adversary controls when you switch between them, you can still make it go unstable. So an argument that says that two mechanisms are, you know, giving nice properties, if you put them both in the same system and let people use them both, then you basically lose all the properties from the combined system. And so this is an exploration of a whole system. And what we can do is try things out and see what happens. And most important results for us here are really going to be around the general sustainability of the proposal counts, the fact that the prices that are observed in the simulation stay on the invariant, and then just generally that the funds, the reserve, and the supply stay in the same order. So those are changing in the lower right, but they're not radically changing. And we have a you know, observation of the effect on the price. Because there's a bonding curve that dictates the price, we can see how it evolves. And here it goes up by somewhere between 5 and 10% over the period of the simulation. And that is one of my main examples, and we'll go to questions again.
Yeah, anybody a question? That was a lot of content.
Yeah, I was curious about the parameters.
What was that?
I was curious about the parameters. Could you describe about like what did you measure about?
I can't hear you very clearly.
Did you ask about the parameters? I also couldn't hear it acoustically.
Oh yeah, I asked about parameters.
Yeah, so actually this system has a parameter sweep mechanism built into it. So I have a bunch of parameter choices in this individual run, but if you look carefully in the upper right, there's a dictionary where I have a whole bunch of variables. All of those are actually stored in a way that you can run multiple controlled experiments where you change those parameters. In particular, this was one simulation in a set where I was varying alpha actually. So we see this with alpha is 0.5 as the example, but we ran it with alpha at 0.5, 0.2, and 0.1 in this set of experiments. We can also run Monte Carlos, but the results are highly sensitive to parameters. But the issue is that you have to get a system that sort of works at all first. So a lot of times works at all means you're kind of playing around with it somewhat, like, oh, trying things out and running it and seeing what happens. And once you get to something that works like more or less how you want, you have to really start to zoom in and use the parameters and as tools and run controlled experiments to figure out what parameters you want. And I will caution against over optimizing them. In fact, I advocate for using the parameters for robustness, not for optimization. So robustness in this case means that you want to pick parameters that give you good results, even when the things that you don't have control over have a wide range of results. So you're actually running mixed experiments where you take random processes and putting them in the uncontrolled elements and running Monte Carlos so that you can see lots of different realizations of those random processes. And then on another dimension, you're trying different values of a parameter in order to see whether, not just whether the parameter on a one-time run works well, but actually how well the system holds up to variation given that parameter set. And the systems get somewhat complicated. It can be multiple parameters that have, you know, non-trivial effects on each other. So, you know, one parameter might seem great at one value, but if you don't also account for other parameters while you engineer it, you could also end up in a weird spot. This stuff is actually so sophisticated that we even have functions as parameters. So that's why the trigger function is blown out here, is because the trigger function itself is a parameter. It's even though it's a function, because it's one of the most important design elements. We needed to be able to say, run A/B tests, where we say, well, what if the trigger function were this? What if it were that? How much does that influence the system? Does that make sense?
Yeah, I got it. Thanks so much. Sorry, I'm a little bit noisy here. I'm in coffee shop.
So, Jonathan, should I hand back over control so you can do the Protea discussion?
Yeah, absolutely. Thanks for that question. Are there any other questions? I think it's good to stop here a little bit. I also wanted to see where you guys are at with your modeling, right? So I've seen there's, for example, altcoin fantasy, right? You gotta have probably quite a bit of modeling to do. I don't know if anyone from altcoin fantasy is on, and also the other projects. It would be interesting to hear how you go, where you are in your modeling work, and what your experience are.
So unfortunately, the guys from Altcoin Fantasy could not join us because they're in Vancouver. So their time zones are a little crazy right now, kind of like 5 a.m.
Got it. No worries. No, I would have been interested. That's a very cool project.
Yes. Yeah. Although we do have a few others here, so I think we can go through. I think we have guys from, especially Dave Polkascan. I'm not sure whether he's going to issue a token, but Sota himself is going to help other projects build their own blockchain. So I think having a lot of this engineering mindset and mechanism designs can be highly relevant.
Yeah, to elaborate, Shikai, for Polkascan, we're not issuing a token, but it's just main interest in the subject. So not planning to work with it, but still we can learn from it and maybe apply some of the concepts in other parts of our business. So you won't hear too much from me, but whenever I think there's a question, I'll just pop up and you'll hear me.
Okay.
Awesome. Thanks, Dave.
And also we are planning to do the ICO maybe next year. Depends on the regulation. So I'm very curious about crypto economics. So this is very relevant for me.
That's great to hear. So the last part of the third part of our presentation is really very practical, and you can also ask questions. So let me share my screen, and then we can go on. All right, now it should come up. Okay, great. I don't know how many of you had the chance to read the article that was also, I think it was pre-sent. We wrote an article last week about CAD, and the goal really of this third part of this workshop / presentation is to make you aware of the tool that we're using to simulate and design these complex systems. And also that it's going to be, or it already is freely available in case you wanted to try it. We have a beta program. So really, this third part is to go through what this tool is, what we use it for. Give you one or two examples, show you how other projects are using it, so you can see whether that's maybe something that you want to check out. There's other tools out there. We tried all of them. At some point, we just came to the realization that we need something that is unified enough, flexible enough, and also integrates with all of the other data science tools that we're using. So we just built it ourselves. So this is the article that I was mentioning. So you can check it out. It's on Medium. So CAD is a Python library. It's specifically designed to fill a gap in the open source Python stack. There was just simply no tool out there that could adequately represent the systems that we were commissioned by our clients to build and test and validate. So we built this tool, and it assists in the process of designing, testing, and validating the systems. as we've shown earlier in the presentation as well. And if you're comparing different systems, right? So I think the closest to CAD/CAD in terms of the flexibility is probably MATLAB, but it's a very different environment, right? Probably most of you know MATLAB. CAD/CAD can also handle systems really at any level of abstraction. So you can do system dynamic stuff like very macro level analyses, but you can also go down to and build the micro foundations of these systems. And this is really what the engineering process is all about, right? You want to decompose the complexity and build it right up, and then wire it all together and see what the system does. And really you can do this with CAD/CAD in one tool. This was very, very important to us. And I think it's fair to say that we saved probably months by now. So BlockScience has been up and running for about 1.5 years. We've done between 15 and 20 design projects so far. These are all longer projects typically. And it really saved us immense amount of time. In the earlier projects, we just had to write all of these experiments that Dr. Zeringen was talking about, and these iterations, we had to write them manually, and it just takes immense time. And here with CAD/CAD, you can basically just, you build a toggle or something, and then you do parameter sweep and go through different parameters, sort of in a grid search approach. Versus doing them manually, so it's much faster. So this is what it is. So we have a toy model up. This is also something currently it's all sort of permissioned in the closed beta, which demonstrates what CAD/CAD is and how it builds models in a very easy way. So I just wanted to give you this so you can take away something concrete, very easy in terms of how do you go about building a system in the CAD/CAD style. Let's put it this way. So this toy model, robots and marbles, it literally has robots and marbles. And on the left hand side, in the first step, typically you try to get your thoughts, your idea, you try to conceptualize them and make them more tangible, put them down into some sort of representation in a graphical sense. So either you go on a whiteboard or you have one of these charting tools. We are developing our own methodology. It's not published yet, sort of, but important to put it down on paper. And here in this system, it consists of two boxes. There's box A and box B, and they all have marbles in them. One of them has 10 in them in this state, and the other one has 0. And there's a robot, and the job of the robot is to take marbles from one box into the other box until there's an equal number of it. So you see, it's extremely simple, but it explains the concept quite well. So after that step, we typically try to map that system into what we call a mechanism graph, which is really taking that abstract idea into a more formalized state. So I'm going to show you a better example soon, but basically we call it swim lane graph as well, because it has 3 lanes. The upper lane, their behaviors, the middle lane are mechanisms, and the lower lane, they're the states of the system. So this represents basically this state space framework that was also referenced and described earlier. And once we have the system represented in that form, basically it enables us to code it up in a CAD/CAD configuration file and then run experiments on it. So here, for example, you see that that system was simulated across 10 time steps, and what the robot basically does is it takes marbles from box A into box B until they're basically equal. And because it was 11, I said it was 10. This is the uneven example. It ends up in an oscillating state, right? So this is very easy, and you could have easily, obviously, reasoned about this. But typically, in these dynamical systems that are a bit more complex, it's very difficult to reason about the system behavior without really simulating it. And this the library that we've built, it has quite a couple of features, right? So I mean, this is sort of the basic feature you can describe and then run the system, but you can also introduce stochastic processes and then understand the variations of the dynamic system model as a result of these stochastic elements, right? So you can, for example, put in unknown cost of production or unknown user demand, and then run 1,000 Monte Carlo runs where the parameters sort of within a sensible range, and that gives you an idea of how the system can evolve. It does parameter sweep, for example. It can do A/B testing, so you can test two different models. We're going to see one example in a minute, to see which model version, for example, fits better with your design goals. We're working on a system identification a functionality which basically allows you to use the input and output signals of your real world system to fit them back into the model and estimate the values of adjustable parameters that you have. So it makes the model better and better over time. So we really try to build the perfect sort of library to get our work done. Yeah, we're open sourcing it. Let me know if you have any questions here. So that was the easiest. I wanted to just show you that this really gets much more complicated. So this is a mechanism graph of a blockchain network. I think it's not client sensitive. No, I took it from somewhere that where we're safe. So I was just looking quickly if there's any client names on it. But basically, you can imagine this. If you think about electrical circuits, right? Electrical circuits are basically systems of electrical components like capacitors, resistors, transistors, and you can think and they're wired, they're connected through conductive materials and wires and so on. And you can think about these mechanism graphs really as business logic circuits that have three different layers and basically represent a protocol, in this example, a blockchain protocol, and the mechanisms that are included in that protocol and that are driven by behaviors and all of that over time. So there's a little bit how to think about that. And it's really a critical step to represent the system. Is a critical step for us to represent the system in this way in order to be able to not only like code it up, but to also ask sensible questions, which is very hard if you don't really formally specify the system. And asking the right questions really is obviously critical for getting sensible answers. So the next topic I wanted to speak about is what we call flight simulators. There's another article that we've written. It's called Introducing CAD. It was, I think, 3 weeks ago. That introduces what we call the engineer and pilot loop. And without going too much into that, you can read the article. So we're trying to really build versions of CAD that can be just used by business users who just want to have insights into a system and want to basically steer a system. So I want to show you one example here that we've basically put in a web app. It's an illustration. It's not a real system, but I think it'll be instructive. So this is a model of a three-sided marketplace, right? So you can think about it like Uber. So there's consumers and there's providers. In this example, the producer, that would Uber would be the producer in that sense, is sort of represented by a community. So this is sort of a decentralized platform business model. Yeah? And we basically, this is the first step if you think back into the three-step process. So we represent it in a graphical manner. The middle step is right now it's missing. I'm going to show you that in a second. So the mechanism graph is the second thing. We did that, and then we coded up a model, and then basically what you can get in the web app is just the output. So you really see the outputs of that dynamical system, and can try and spot things that you find interesting. You might want to tune, for example, the volume of production, or the price of the token, or the fiat reserve and token reserve in that system. So what I wanted to do is quickly just jump here into that web app to show you that it's really an illustration here. So the parameters you can set there. So for example, you can set the token supply, you can set the maximum number of transactions, starting token supply at the start. But let's just run it. And here at the bottom you see the mechanism graph, so you can go through this if you wanted to. So this is, we always
Jonathan, you're still showing PowerPoint.
Oh, is that right?
Yeah, you got to switch to your browser.
Oh, okay. I didn't know that. Thanks.
Yeah, I thought you talking before switching.
Okay. Okay, sorry. I didn't know it was just showing specific windows. Do you see it now?
Yep.
Yes.
Awesome, cool. So it's a simple web app, and here you see the mechanism graph. If you wanted to check that out, and then basically you can dynamically. So you can imagine, for example, if you run a project that has a big community, you can. This is a digital twin of a system, right? So you can basically create that digital twin of your system, and then put it out there, and let your community play with it, right? Or let investors play with it. Really create the ultimate transparency of the system dynamics. Of the system you're building, and we think this space will move into that direction, right? So in the future, we do believe that there will be much more transparency about the dynamics of specific archetypes of systems and of specific systems, and also that the creators of the systems will have to provide that transparency in order to gain the trust of investors of the community.
I want to add a point here too. There's a lot of discussions about governance in crypto that are relatively ill-formed because people are uninformed. The reality is that governing a crypto system is essentially equivalent to preventative maintenance of a system. But you can't do preventative maintenance if you can't see the health of the system. And so the health of the system goes beyond just statistics about it, but actually the sort of consequence of that state. So the idea here is that if you have these digital twins and you have the sort of real data from the system, that you can do sort of the past to the current state, and you can do projections into the future under a variety of conditions. And when you want to make changes, when you even make decisions individually, that they can be informed. And it's not to say that everyone's going to be looking at them all the time, though. I mean, given the way people interact with CoinMarketCap, you never know. The reality is just that we recognize the sort of similarity between the community taking part in these systems and sort of communities in less technical senses, where you kind of have to have a pulse of the health of the community in order to be a real participant, and especially to govern. So I'll give it back to you. But this is, in my opinion, just like critical path for the maturation of the space towards sustainable things, because with systems like this, if you don't have an understanding of how they'll behave, it's very easy for the tyranny of the majority to drive the system in an unhealthy direction, while at the same time perceiving it as a good thing. That's a really common failure mode in social and economic systems, sort of herding towards undesirable equilibria or herding towards failure. And we can only really offset that through transparency.
Great. Thank you. So let me switch to one example here. So we run this beta program. Let me talk about the beta program first. And then I'll show you one case of a beta program participant. So we've started to officially, get this out to projects that are serious about modeling their and understanding their systems. There's quite a couple of them. So it's a group of about 60 system engineers. It's very much permission. So one has to apply, and it takes like 15 minutes to apply. So there's really quite some friction to only have people who are really interested in also going through the learning curve of learning a new tool like CatCat. Even if you know Python, there's still a learning curve. So what these guys get and why they apply is they get access to CatCat, while others, might have to wait half a year until it's really open source. We're, finishing up, getting feedback. But this private support community has been very useful for many people. So many people, they have, a question: how do I integrate another Python library? Like how do I display my CatCat results in Network X, for example, and look at my system in a different way? Or how do I analyze it? Probably you can analyze it with machine learning libraries like TensorFlow and so forth, right? So there's this discussion going on. So that's what it provides. We try and post regular beginner tutorials. So for example, there's CatCat, robots and marbles. That's sort of something that we came up with in order to help people get over that initial sort of hump of understanding. We've also done sort of half an hour or even longer support calls. Although this, obviously, besides our commercial sort of work, gets quite tight time-wise often, but we try and do our best. And we also take projects like, for example, in this call, and then just talk about them, right? So if they build on CAD and they making use of it, like Protea, then we can also take these projects around and talk about them. Obviously, these are a couple of examples that are building real systems. So, for example, the University of Zurich, they have a project called Finance 4.0. They have like 2 PhD guys building with the Clovers. They will do a big presentation, I think, in 3 weeks about their system. They're already running like 1,000 Monte Carlo runs every day, and we have to upgrade our service because their models get too complex. So basically the idea is, if you guys are interested in checking out CAD, then there is this beta program, and we're excited to see people, try and understand their systems better than the average project in this industry. So now I wanted to quickly go through one use case, which is Protea. I'm going to make it quick because we have time for general questions. Let me do this. Okay, so you should see. Do you see Protea now?
Yep.
Awesome, cool. So we've put together this little thing. So Protea is a project. It's quite interesting. It comes out of Linum Labs. Linum Labs is sort of a lab that spits out awesome blockchain projects in South Africa. And Protea builds infrastructure for decentralized communities. And they were one of the first ones to jump on this because they realized that their protocol has lots of different pieces. For example, a user growth module and a token bonding curve and a taxation model. And they used CAD to really wire all of this together into one notebook. And they also, because Linum Labs is very focused on proper professional token engineering, they also, together with us and a couple of others, kind of grow the global token engineering community. They've integrated CAD really into their process. So before they deploy any contracts, they validate them with CAD. They also deploy in Python, so it's quite convenient for them. And then they use real world data. They're also still in the process. I think they're live now since a couple of weeks, but their process looks like that they will integrate real world data into the CAD model and then iterate and try to understand the system better and better, as was mentioned earlier in today's talk. And this is really our goal. We think tools like this need to become standard practice. And we're seeing this now in our beta program. We're seeing this in the token engineering community. I don't know if you follow the token engineering Berlin guys. They're really building. They already have, I think, 18 countries and like weekly global calls and so on. There's really a momentum towards this professionalization of the space. Protea also ran concrete experiments. So I think the first thing that they did is just represent their token bonding curve. So far, they haven't represented their entire protocol, but the token bonding curve, they have a CAD model of that they've presented in a call that's also freely available. And they played with different user types, like these are different people buying into the bonding curve and also selling, obviously, different mechanisms and different policies. Actually, I haven't seen the policies so much yet, so I have to verify that still. But basically, the first insights that they presented in a recent community call is they wanted to see how do two different bonding curve designs, right? So you can see here the linear functions, and how do the two different designs differ in terms of the value, the token value for a specific user group. So typically in these systems, you look at the collateral pool, right, and user balances, and they wanted to look at user balances and check like what happens if the whales would like sell off, and then they realized because they had this CAD model that in the left kind of design they had a much more negative effect on the user balances than in a different alternative design, right? So it probably would have been possible to reason about this still, but this is just an example of the kind of experiments that we see projects run in our beta program. And it's step by step. They go component by component, and then we're helping them wire this all together. But we're seeing real insights and real design changes happen because of insights generated through this type of modeling.
One comment about insights that I think is important for people to understand is that the best ones are obvious after the fact. So you still hear Jonathan say something like, well, maybe you could have reasoned through this. And what you have to remember is that, like, that might be true, but that realizing it in the first place is a much bigger challenge. So I generally like to point out when something is determined through computational experimentation, and then afterwards you're like, oh yeah, wow, that totally makes sense. That's actually a really good indicator. It's something that happens when you've uncovered something somewhat fundamental, but we just have to be aware that that doesn't mean that the best path to that insight was to sort of just think about it, because you don't have as much surety behind it. So it makes sense to use your sort of computational tools to uncover those insights, and then to use your reasoning and your gut to sort of fact check it. Like, does this make sense? And like, go through that iteration. And the ones that are really obvious after the fact are really the best ones.
Yeah, that makes sense. That makes a lot of sense. Yeah. So this was, I just wanted to give you sort of a flashlight of what's happening in our beta program and why so really they're quite excited about the tool, because they basically say it, like, actually we just did this recently. They basically said CAD is sort of the glue for previously disconnected components. And so we're also learning how this tool can become useful for different projects. Although we've used it for a year in own projects, we're still learning. So this is something that you can look at if you want to. It was basically meant to be an example of real projects that are live today, making design choices based on computational simulation and insights derived from these. And that's sort of, we have a couple of more case studies, but I think given that we have, just like 20 minutes left, I wanted to maybe, stop it here and open a very general like Q&A. Like, you can really ask us anything, it could be about the presentation, it could be about CAD, it could be about, token engineering in general. So I'll stop here, and yeah, thanks for listening through all of that content.
Thank you so much, Jonathan and Dr. Sergen. I'll leave the questions to the guys.
Can I ask a question?
Yes, go ahead, Sota. Yes.
Oh yeah, so it's not related to maybe this session. So I'm curious about what is the best token design you have ever seen in the blockchain space?
That's a very good question. I think one of them that we're quite proud of is one that we've actually designed ourselves. I don't know, Sergen, if you want to talk about your two-token system, or if you have any others that you find particularly well designed.
I mean, for me, I'll talk about maybe not the two-token systems they tend to vary a lot depending on the objectives of the system. And I think a lot of people understand that you need two separate pieces of functionality when you're dealing with sort of medium of exchange, sort of stablecoin systems that have some other programmable aspect. Like, we often see these systems with, like, whether it's a bonding curve or other mechanism, decouples the sort of global notion of money, which, in an Ethereum-based system, I tend to default to DAI, and the local economy, the programmable asset for a specific group. So I think I'm actually going to leave that one and talk a little bit about, there was a design that I did 2 years ago for Sweetbridge, which was, they called it the discount token. I don't think that's the best name for it. I think, and I actually didn't really get as much traction because of sort of a pivot in that project, but the design is actually my favorite. It was probably the first real embedded invariant design that I did, and it maintains a revenue share over a global community. So in a nutshell, you say there's a fiat price list for a set of services, like a license fee or basically any fiat-based cost model for a service. And then you say, for any transaction where you would pay and say, say DAI, like assuming that we're doing it on a smart contract, we have a fiat representation, you do a transaction where you also stake or lock tokens that are the community token as a assertion of your membership, of your participation in that community, and you get a discount. But that discount is not just meant to be a discount. In fact, you could get the service entirely for free if you lock up enough tokens. But the catch is that the amount of discounts that you get, or how many tokens you would have to lock in order to get it for free, is controlled by a sort of embedded controller that is based on the ratio of revenue being generated and the total number of tokens being asserted or staked. And what this is essentially doing is recreating a co-op model where all of the token holders are stakeholders in that community. And if non-token holders are spending lots of money on the platform, it becomes quickly very easy for all the token holders to get the service for free. But on the flip side, if a very small number of non-token holders are using it, meaning the token holders themselves are the ones using it, then the discounts are much smaller, because what it's doing is preserving the share of the total revenue generated. So if you generate $1 million worth of revenue, and you have a parameter set at 50%, then you actually generate $500,000 worth of revenue, and that other $500,000 is distributed proportionally to the tokens locked for all of the users. And so what's happened for all of the community users, the ones that are actually locking tokens to assert their membership. So what ends up happening that I find really interesting is that, like, if you can get a big user base that's just like, you've made something that the outside world wants to use, then those people are ostensibly paying full price. They're pushing up the total revenue and making it free for all of the people who are inside the community. And like I guess, I mean, you asked about one that I'm particularly proud of, like, or like, think is a great design. I think that's really important and powerful because it interpolates between the system when it's in its maybe nascent days, where all the users are just the creators and there's not necessarily a lot of external value creation yet, and like later the potential value of those tokens and of that asset goes way up when it's adopted, and it's the users who created it who are getting it for free. They're having this asset that is actually, mathematically growing in value because actually it's defined in terms of a proportion of revenue. If that revenue is going up, there's actually an intrinsic value computable relative to the revenue generation, which is if the product, the software product or whatnot takes off, then it goes up. There's actually a white paper from maybe a year and a half ago with math proofs in it about that algorithm that's public. I think Jonathan can probably circulate it. You have a copy of that paper, right, Jonathan?
Yeah, I can include it in some information we can make available later. Yeah,
it's also posted online by the company that we did the designs for. It's openly available, and they actually had it designed for they were at the time planning on sort of launching an ecosystem of partners with their own tokens, and were advocating for others to use that token model. So it wasn't designed privately. It was designed as a public good for people to use for designs. And it was one of the precursors to the CAD modeling, because we built a bunch of custom models without CAD, because it was like 2 years ago, to demonstrate all of the phenomena. And then we actually refined CAD and designed what CAD would be, in part based on all of the things that we were doing manually without the extra engineering tools to do that design. So it's actually kind of cool. The paper doesn't have the simulations in it. It only has the math proofs and the descriptions. But I definitely think that it's worth checking out. And I'm hoping to see that design make a resurgence in the future. But obviously I only advocate it for people where it like fits their needs. Because at the end of the day, token designs are not like copy pastable. You need to be able to fit them to your specific use cases. But it's a great building block.
Got it. So it's very interesting for me. So I will look through it and also Katakata too. Thanks.
I hope that answered your question. I was thinking you're hoping for like Libra or like Binance Coin or something like that.
No.
As engineers, we can't speak in detail about systems that we haven't built and that we haven't simulated. So we speak about the ones that we did build and did simulate.
Yeah, but the answer was perfect. But I'm very curious about Libra too.
Well, to be fair, I mean, besides the fact that, I mean, they released a white paper, but Libra is just basically the consensus is, Byzantine fault tolerant in the general flavor of Casper, and the overall system is a consortium model, which is pretty like consistent with most of the enterprise blockchain designs for specific ecosystem. Like I worked a little bit on an ad tech ecosystem, and I looked at, like, I've worked on a couple, obviously, like more enterprise focused projects, and the pattern for an enterprise consortium is pretty well known. So nuts and bolts of it is that Libra is a sort of a play for a global stablecoin that is defined basically with its consensus looking like a lot of what we see in the crypto consensus R&D and with the public teams, and then its miner base or its steward base is just a corporate consortium in a similar style to others. They didn't really do anything novel. They just took the best parts of what they saw out in the world and sort of synthesized them into what, basically something that met their objectives, which I would say from an engineering perspective is great. I still have my like sort of, not sure how I feel about Facebook taking the lead on launching a global currency.
I see. Interesting.
Any other questions, guys?
Excuse me. I think formal verification like OCaml is similar to your product, but your CatCat is designed to verify not only for program but for protocol or design. Is this right?
Kind of. So we actually have a slide. Jonathan, do you have the verification and validation slide? So what you have to understand is that validation and verification are not the same thing. They're two parts of the same overall engineering process. So the formal verification work that people are doing is also part of a proper engineering process. We are just not focusing on it because other people understand and are already doing it. But verification is inherently internally looking. It's about making sure that you implemented the thing that you declared correctly. Validation is outward looking. It's like does the thing I made fulfill the right role in the system that it's part of? And so when you're taught the verification and validation in engineering, you're kind of taught to understand how to compose systems like layer over layer, and you have to basically, for anything that you create, you need to be able to verify that it was implemented correctly and validate that it fulfills the right function in the system above it. And those are sort of like a fractal pasting thing. So you take you verify and validate, and then that thing that you've created can sort of be embedded in another thing. And then you can kind of validate and verify, which sort of allows you to embed that in another thing. So whenever you're doing sort of systems beyond one layer of depth, you actually have to do both. And most of the crypto world is much stronger at verification than they are at validation, because verification is taught in the computer science and sort of software development training, and validation is not so much. So we're basically filling in the other half. I think maybe the best way to give an example is with circuits also have validation and verification. When you build a circuit, your verification is making sure that all of your basically all of the connections and all of the resistors and capacitors are all in the right place according to the specification, and that the system is actually correctly implemented according to the specification. But it tells you nothing about whether the specification was actually suitable to achieve that system's goals. So a concrete example of that is I did a project once when I was much younger where I made a circuit to do a control system to manage the light level in a sort of a sustainable design project. And it actually had a very specific purpose. Its job was to modulate the level of light output by a battery of LEDs in order to hit a specified level of light on a work surface. Now, getting a design for the circuit was a mathematical exercise followed by writing out some equations and saying, here's the circuit that I want to build. That was design. Then I had to put it on, make a circuit that matched that. And verification was cross-checking whether or not my design and my implementation matched. But actually whether or not it worked in the sense of the system it was part of actually required me to wire it up to the lights, plug it in, turn it on, and run tests at the sort of level of hey, am I actually hitting the light densities I want? And that was the sort of verification of the final system. But if we backtrack and realize that I made a circuit to do a control system, if I had designed it wrong and implemented it correctly, and it wouldn't have worked at the end. I had to test that actually using computer programs. I actually took my design, I simulated it first because I didn't want to take the time to even implement it correctly if the design was wrong. So there's a really strong distinction between validation and verification that often gets lost unless you have an actual engineering background where the implementation and the design are a little more decoupled. And with the crypto systems, we're moving into a level of complexity where that separation starts to matter. You could design a smart contract with a set of incentives and totally correctly implement it, formally verify that it's been implemented correctly, for example, and still not get the intended behavior at the system level. Does that make sense?
Yes, thank you. I stood very well. Thank you very much.
And I have, this isn't quite the one I was looking for. Jonathan, I think it's in some of our CAD articles, so maybe we can highlight it.
We can include it in the pre-send, in the post-send materials. Yeah.
Yeah, because we made a grid that actually fleshes out practically how that workflow looks, and it includes both the verification and the validation steps, so that to try to help them not get confused with each other.
Yeah, there's one question here in the chat. Zergem, that's one for you. Can you elaborate on the work done for Polkadot and share any findings or conclusions?
So the short answer is not really. We just kicked off the project, and we're kind of, the relationship is one where we're doing sort of validation again. So we're like going through designs and sort of seeing how they fit together. And so it's sort of our job to first order, like do that analysis and sort of deliver it to them and let them make any choices, decisions, or changes that they might want to make as a result of those analyses, and then sort of publish the results on their timetable. So I can't actually go into details about it. I can tell you that I'm excited about it. I think that the sort of network of networks approach is critical, that it doesn't make sense necessarily to have, one blockchain system. It's not scalable, but that even the sort of sharding and like attempts to make an individual blockchain scalable are not like at the level that we need, that actually something where we have multiple chains able to talk to each other is actually much more appropriate from a first principles engineering design perspective. I know that's not really your answer to your question, since I'm not talking specifically about what we're doing, but I will say that, like, going back to my power grids example, like a power grid isn't one grid. It's like a grid of grids, like different entities owning different parts of it and interacting at different points, and they're systemically interconnected, and those interconnections have to be managed. But ultimately what makes it a scalable decentralized system is the fact that it's not all managed and maintained by only one one group. I guess it's harder to explain. Human systems are a little fuzzier, but this network of networks architecture that you see in Polkadot and also similarly in Cosmos, I think are sort of critical path evolutions of this technology.
Cool, thanks.
Anyone else? Okay, actually, I had one question for you guys, if you don't mind. think before we had this the really engineering mindset that the industry has been quite obsessed with, token velocity and how they can, reduce the velocity of things like staking, burning plus minting, and then they came up and they also wanted to solve the volatility problems. That's why they came out all these like stable coins, dual token mechanisms. Were those headed in the right direction based on like the analyses that you've seen? Or are they like completely misguided? We don't need any of these mechanisms. And do you see any kind of new mechanisms come up based on validation? Did it like inspire some new ideas?
So a couple answers since you asked a couple questions. So for starters, the sort of velocity analysis was a little bit, I'm not a huge fan. I think that it was kind of misunderstood and misused by a lot of people. There's two separate notions of velocity that are that have very different effects on a system. So there's internal velocity, which is circulations, which is what is traditionally associated in economics with like, the equations that you see in where like the velocity of money in an economy is the number of times it turns and it passes around within that economy. The velocity issue that arose in crypto is actually very different. It was the flow in and out of the economy. So if I'm trading, say, Ethereum for Bitcoin, you could argue that I'm moving money from the Ethereum economy, value at least, from the Ethereum economy into the Bitcoin economy. And more importantly, with like, fiat as the sort of main anchor, you'll see people literally converting into a crypto asset, spending it, and then the person who got that converting it back out into fiat. So that like is not the same kind of velocity. That's like through velocity. It's in and out. And then that's very different from internal velocity, which is like, given that the funds are in a current market, so say Ethereum, the same Ethereum, how many times does it get spent? So because those are two completely different concepts and they actually tend to have opposite effects on a system, the discussion of velocity has been completely confused and almost useless. Not because the concepts were wrong, but because people just didn't know how to understand or apply them well. So the people who brought those concepts out, people like Chris Bernitzky, used them fine, but the general public used them very badly. So that it kind of prevented it from being useful. I think it could have been more useful if people understood it better. In terms of volatility, I think it's actually really important, but I think that we've been managing volatility in the context of using tokens as medium of exchange. And I think that the two token models are actually very important, that we have to recognize that tokens aren't just money. In fact, I prefer to describe them as atomic units of information. An atomic unit of information can be used to denote money, and it's a valuable thing to do, but it's far from the only thing that makes sense. And so we have to do a better job continuing to flesh out the different use cases for these provable atomic units of information, and recognizing that it's probably good enough to have a relatively small number of assets that serve as medium of exchange. And you have even different types of assets that might make sense as stores of value. And then you have another notion of like everything else that you might do with a programmable asset. And we made this really kind of shitty thing where everyone tried to inject a token into their protocol, into their product, and it just had this proliferation of bad UX because it doesn't make sense to have to think about all of these extra things. So we end up designing systems to abstract those tokens away, which lead to this sort of throughput velocity problem. We end up using stable coins as a way to sort of shift away from that, and I think it's helped a lot. The problem is then what's left, right? Like people are like, okay, well, what is my token really for? Do I really need a token? And the answer is often if you design the system so that there's some need for what I'm gonna call a sort of atomic unit of information to keep track of the way that value or activity is flowing, then you may still need a token, and you may be able to make it a token that increases in value in certain ways proportional to the actual uptake of the network, not necessarily proportional to the uptake of a market per se. You kind of manage or control the pricing directly if you have mechanisms that assert how one transforms a unit of stablecoin into a unit of token as a function of network state, And that network state can include measures of adoption. So like, numbers of transactions or other types of, data that is present in the state of your system. So there's a lot to unpack there, and I realize it's more than I can go into right now. But the short answers are, velocity isn't a bad concept. It was misused and misunderstood. Stablecoins are actually really important pieces of infrastructure because we want people to experience money as money for the most part. And then the last thing is that the way that the stablecoins interact with the sort of local economy programmable assets gets a little bit more sophisticated when you can't just say, oh, well, it's just money. It's not really just money. It's something specific related to what you embedded in that ability. Is it a governance token? Is it a, basically anything that you come up with that's context specific that causes people to need it in order to participate. But participate is different from pay.
I see. Thank you. I think that's definitely very insightful. If are you guys very tight on time? Do you have to really go on time, or do we have time for kind of maybe a little bit more questions?
I can do a few more minutes. Jonathan, how about you?
No, before you joined, I said we can go a bit over, but actually I hadn't checked your calendar, so let's take 5 more minutes or so. There's no worries. Yeah.
Yeah. So if you don't mind, I have a final one. Of course, I think a lot of people are very obsessed about the prices. We are more focused on the technology, but I mean it's an inevitable part of the ecosystem, right? So I actually am curious if you actually found a more scientific way to value like a token economy or like a token ecosystem rather than the current way of like
so
valuation.
Yes, yeah. Yes and no. 2 things. First one is the yes with the strong yes is we basically built the same kinds of CAD models that you would use to model markets irrespective of whether they're crypto markets. It turns out that if you build a CAD model of a stochastic dynamical system, you can reproduce the kinds of behaviors that you see in markets, crypto and otherwise, because it's primarily driven by the composition of strategies in the market. So you have 3 really important groups of strategies. One are essentially noise traders or herders, people who mimic the current trends predominantly, and they tend to be sort of low or high frequency traders who are not very intelligent from a like systemic perspective. They're just like trying to get those short-term gains on the current trajectory. And then you have efficient markets hypothesis, or people who are trading against some belief about the price or about the belief about the sort of underlying signal that the price represents. And those are the people who we generally associate with rationality and the ones who are running algorithms or behaving in a way that is sort of theoretically optimal. And they have another effect. And then there's a third group, which are sort of those who have some private signal or some internal knowledge about maybe something that's not public. And they're essentially signal traders, or they have this, like, we don't necessarily know what those private signals are, but they're the ones that drive the system. And so what ends up happening is that you don't have to count the number of people trading in the strategy pools. You need to keep track of how much of that current assets being traded are being managed according to that strategy type, because that creates a much lower dimensional model where you can see it like subpopulations. And then there are gradients of flow of value between the groups depending on certain things. And in particular, you see, for the most part, the really short-term herders are like, they're injecting a sort of volatility into the market. So if there's a lot of them, you get more or a lot of money managed by people like that, you get a lot of volatility. Shockingly, crypto has a lot of those people and therefore has a lot of volatility compared to the more efficient markets hypothesis, which tends to suppress volatility because people are arbitraging the degree to which the system has moved away from what the sort of, we'll say the rational person would estimate the value to be. And then you have those signal traders that are actually often driving the underlying signal. So even the efficient markets people technically lag the response to the signal traders. So if you model the system as having some signals in it that that aren't known by everyone, it's those actors who act in response to the signal that they know who are often the best off, but it's often by far the smallest group. And so you can create models of markets with CAD, this system framework that we use, that reproduces the kinds of results that we see and allows you to run projections and get estimates. But unfortunately, that's still just really a model of how market dynamics work. And at the end of the day, it's driven by that underlying signal. So the know is, yeah, cool, if you know what the underlying signal is. And actually, so in order to be good about design, one of the things that we think about is like, what can or should be that underlying signal, which is part of the reason that we use bonding curves, or even in the discount token, I described this notion of an intrinsic value that's actually a real thing that was designed for. It's a thing that has a price as its dimensions, but it's not the secondary market price. It's a ratio of tokens to fiat value that is designed into the system. It's the sort of per token staked per period, fiat offset. Well, if you can save X amount of dollars per token staked per month, you're creating a sort of floor price that says, hey, like it really shouldn't drop much below this, because you can always buy it and use it to offset that much, but only as long as there's demand for the service that's offsetting. But it does create a notion of intrinsic value, which in turn becomes the source of the signal. And if that signal is public, you can imagine the whole market becoming a little bit more stable, because instead of having a small group of people being signal traders, you could imagine the wider market being generally aware of that signal. And as a result, a much larger fraction and thus a much tighter band around that signal. Next question is, how volatile is that signal? That comes back to your token engineering design. How is it something that's going to be noisy? We've looked at different ways of inducing low pass filters on those very signals to help prevent a system from being volatile. So the yes and no is that, look, we understand how these markets work, and it's because they just work like other markets. They're not actually special. The differences in their behavior come from the differences in the composition of the capital and the strategies associated with that capital. And then the fact that the signals tend to be, themselves somewhat noisy, because they're essentially early stage products being IPO'd. So they also have more volatility. So between the volatility in the intrinsic value in the signal itself and the magnifying effect of the high degree of herding behavior, it's very actually easy to systemically recover why crypto markets look the way they look, but also that means that we can hopefully design for systems that aren't quite so volatile in the future. Does that answer your question?
Yes. Thank you very much. I think the implication of it behind it as well is that when you talk about the signals and how to value the overall network by implying that markets are the best way to do it, it means that you can just take the token price times the total token supply, and that's how you would kind of value the total network value, you could say.
Right. I mean, the interesting thing is that you have this notion of market cap, which is essentially what you just described. But if the market cap is computed against a secondary market price, all you're doing is looking at what is essentially a noisy, potentially very wrong estimate that's driven by this noisy market process. But if you have a more concrete representation of the value per unit token, for example, in the discount token example, in the discount token case, where this is the total amount of fiat worth of services it can offset per period, that version of the value of the economy is a little bit more concrete than this is the extrapolation of the current market price and the supply, because you're not going to be able to realize that. Whereas in an example where the tokens can be asserted for service, like there you're saying that this is exactly how many dollars worth of revenue that the current token supply is offsetting. So it's just a more concrete measure of something that shares the same units, basically fiat per token.
Yeah. Got it. Thank you very much. I think anyone else with questions, or we're about 10 minutes after time. Oh, okay. I think with that, we have to thank you very much again for your
thank you guys
for the very in-depth explanations. We really look forward to the extra readings, which you mentioned the links after this. It's been really an insightful session.
That's awesome to hear. No, thanks all for staying with us for so long, despite the heavy content. So we hope we could pass on a little bit of an engineering mindset to you and communicate where we see this space going inevitably. Shoot us a message at so you can shoot me a message, or if it's easier to do, it's also catcat at BlockScience. You can also take if you want to join the community of system engineers, or if somebody in your circle you think could benefit from that, you can try out catcat if you want to. And all of our stuff that's coming out, we have an article series. If this kind of content is interesting to you, just follow us on Twitter. The handle should be on this slide, but it is block_science. Yeah, thank you very much.
Will do. Have a great day ahead.
Thank you. Bye-bye.
Thank you. Bye-bye.